All right, section 1.2, we're going to start our discussion of limits. Chapter 2 actually is all about limits and finding limits. So in this section in particular, we're going to be finding limits in two ways. We're going to be finding them graphically, and we're going to be finding them numerically. Now, we did a numerical technique at the very end of section 1.1, right, with the tables. So anytime you see the phrase numerically, it means tables. So jot that down in your notes right now. Numerically means tables. And graphically obviously means with a graph, right? So this is graphs and tables. That's what this section is going to be about. We're starting with a definition of what it means to have a limit. A limit is a y value that you approach, but you may or may not touch. There's a movie that has a really good visual description, and it's a funny movie, and it's science. I've got a lot of science people in this class. It's called IQ. It has Meg Ryan in it, and I can't remember the guy's name. It's the guy's name from Shawshank Redemption, if that rings any bells to you, which is also another good movie.
Freeman?
Huh?
Morgan Freeman?
Nope. It's the white guy from
The Prisoner?
The Prisoner guy, yeah, the other one. Can't remember his name either. He was also in a movie called Arlington Road. Anyway, in this movie, she is the niece of Einstein, Meg Ryan is, and there's this point where she likes this guy, and he is asking her to dance, and she says, it's mathematically impossible. Can't dance with you, because you can never reach me. You can cover half the distance, you can cover half the distance again, but you will never actually reach where I'm standing to dance with me. And of course, it's kind of a silly idea, but it is the idea of limit. It's the idea of getting infinitely close to something, but never actually arriving there. So there are three types of limits. The first two are called one-sided limits. So the notations are slightly different. You see a plus sign right here, addition. You see a negative or a subtraction sign right here, and then you see that there's no sign on the last one. Those signs, the positive and the negative, are telling you which direction you are approaching the value from. So on the first, when it says 3 plus, it means 3 from the positive side of the graph, which is the right-hand side of the graph. So it doesn't mean you're moving to the right. It means you're moving away from the right-hand side toward 3. So if you can imagine from a number line perspective, if 3 is here and you're approaching it from the positive side of the graph, then you're actually moving this direction. You're getting close to the value of 3 from the right-hand side. For the second one, the negative, it's the same thing, but from the negative side or the left-hand side of the graph. So here's my negative side of the graph. If I'm looking at the limit as x approaches 3 from the left, like on the negative side, it would be moving toward 3 from the negative side. So the positive and the negative are telling you where you're coming from. The 3 is telling you what you're getting close to. Does that make sense? Then the last one, without any symbol after it, the positive or negative, means you have to come from both directions at the same time. Okay? So you're both approaching like this. So in a very real sense, on the last problem that we did, we looked at approaching the value of 2 from the right, 2.1, 2.01, 2.001. We looked at approaching it from the left, 1.9, 1.99, and 1.999. And when we compared both those lists, we were talking about coming from both directions. Okay? That's the different pieces of limits. So in order for a limit to exist, this happens if and only if the one-sided limits go to the same thing. Ours did on the last one. They both approached 14, right? And I mentioned that doesn't always happen, especially, we were talking about specifically, I should say, with slopes. But with values themselves, this can also happen, where they just don't approach the same thing. For example, we'll do context. My husband and I both decided that we were going to go to McDonald's, but I ended up at the McDonald's on Harrison, and he ended up at the McDonald's on Kickapoo. We would not have arrived at the same place. There was a disconnect, right? We both know we were going to McDonald's, but we went to a different location. Is everybody with me? Okay, so from the perspective of a graph, this typically happens when there's a disconnect when we have a jump in the graph. Right, one gets up here and one goes down here. Another possibility is that you have asymptotes occurring where one asymptote goes like this and the other asymptote goes like this. They're not going to the same location. So if those things happen, the limit doesn't exist. but the limit will exist if they're approaching the same value. So we're going to take a look at a graph. Okay, so this graph clearly has a jump in it, just like I described. There's a disconnect somewhere. But there's lots of places where it's smooth and connected as well, right? I mean, all the way until we get to its -1, it's smooth and connected, and it's very friendly, right? It's just a constant line, at a constant value even. After that, right, after the value -1, it's also smooth and connected. There's only one place where it is not connected, or where there's that jump. So when we're taking a look at limits, we're talking about coming from different directions. Our first question here says, I want to come at the value of -1, and it says positive. What does it mean? From the right. So we're always coming from that side. This is the positive side. Well, I'll move it down. This is the negative side. Okay, so you can start anywhere to the right of -1 for this to work. It doesn't matter where you start. I'm going to use blue. And you're moving, sort of imagine that you're walking along the curve. Okay, so we'll do it visually from over here. So I'm over here, and I'm walking along my curve until I get to, in this case, it's a hole in the graph. The hole doesn't matter, but that's where I'm getting close to, right? What's the y value at the hole? 2. Yes? So that's the limit. It's just the y value that I'm approaching. It does not matter if I arrive there. In fact, I do not on this problem because it is a hole. Yeah? I don't get to 2. All right, this is me getting to the McDonald's parking lot and not walking in. That's what this is, right? I stayed in the parking lot. All right, so on the other side, part B, says I'm approaching from the left. So this time, we're over here, somewhere before or to the left of -1. And as I'm walking from the left side to -1, what value am I approaching? 1. It's always y values. What y value am I approaching? It's 1. Not just approaching it, I'm at it the entire time, right? This is the person sitting inside the McDonald's waiting for somebody else to show up. They're there the whole time, right? We use the phrase approaching because you may not ever get there, but sometimes you do. This one, you're at that value. So its limit is actually 1. What is C asking us? Both. Now this kind of goes back to this over here. The one-sided limits exist, but they are not equal, right? So what does that tell you about the two-sided limit? It does not exist. And in particular, if these two things equal one another, that's simply the answer for part C. If they had both said 2, the answer would be 2. They don't. One says 2 and one says 1, so part C actually does not exist. I will use D and E. It doesn't exist. Now, just because the -1 happens to be this place where it jumps in the graph doesn't mean it's the only one we can ask a question about in terms of limit. So we're going to look at D and E as well. Okay, so on D, we're approaching x equal -2. So that's over here, yeah? And it doesn't have a positive or a negative after it, right? It just says -2. What does that mean then? You got to come from both sides. Now, it may feel a little bit funny. You know, coming from the left is pretty straightforward, yeah? Oops, I went too far. You know, we're approaching this particular location from the left. Coming from the right, though, feels a little bit weird. And it feels weird because, you know, you have to jump. It's okay. You can still make the journey, and then you can jump down and continue your journey. There's nothing wrong with that. Okay? You have to make the jump, or you won't actually arrive at x equal -2. What is the limit at x equal -2? It's 1. Right? It's the y value that you're approaching. Well, you're at 1, so the limit is 1. And the last one we're going to do is at x equals 0. So x equals 0 is the y-axis, yeah? So again, we approach from the left. This time the approaching from the left is the place where I'm going to have to make a jump. So approaching from the left, I do this, and then I jump up to over here. And approaching from the right means I go like this. Now, it's not crossing on a perfect hash mark, so we're going to do an approximation. But what would you guess? What seems reasonable?
2.75.
Not 2. Oh, sorry, yes, 2. I was looking at it wrong. 2.75, perfectly reasonable. If you had told me 2.6, that'd been fine. 2.8, I don't care. But you can't tell me like 3.7, right? And really, you probably can't tell me 2.5. It's clearly more than halfway. So you're somewhere between 2.5 and 3. Does that make sense? Okay, we'll stop there for today.